Hello everyone and welcome to Lesson 3. My name is Gabrielle and today I'll be partnering with Jiwoo to teach you how to add simple animations to your basic shapes in order to create dynamic pieces using functions such as rotation, movement, and color. So to begin our lesson, we're going to first type in our website MacOutreach.rocks and we're going to log in using our username and password that are both case sensitive, and then we're going to click on our animation slot. So that's the second icon on the top row that kind of looks like a moving film strip. I'm going to change it to whatever slot we're comfortable working within. I'm just choosing slot 9 for now since my other slots are filled with other examples, but feel free to choose whatever slot you're comfortable working within. And once we log in, we're going to see I have a code prepared. So I'm going to hit compile and you can see. So for this lesson, we're going to begin with rotations. So in this animation slot, we have prepared a code for a smiley face that is rotating. At first it appears almost static, but if you look really closely, you'll be able to see that it's actually moving very, very slowly. So let's take a look at our code to get a better example, understanding for what is this movement and how we're able to mimic it on our own for our own basic shapes. So looking at the code in lines 1 to 3, this is a comment we made. We're able to see that it details for a movement where 1 degree of rotation equates to 1 second of movement in Elm. Specifically on line 5, we're able to see that we use the forward piping tool to add a rotation function which uses model.time, which is simply the number of seconds since the compile button has been pressed. So now referring to the code here, how long do we think it would take for one full rotation to occur? And remember that one full rotation is 360 degrees. So one full circle. Yeah, so since 1 degree of rotation takes 1 second, 360 degree rotation would take about 360 seconds or 6 minutes. So let's kind of break down this code and see how we're able to manipulate it. So our smiley face is moving kind of slow right now, but if we ever want to speed him up, we're able to just multiply it by a larger number, greater than 1, and it'll move much faster. This is similar to how we used our scale and our move functions to help manipulate them to go at a different speed. But if we wanted it to go slower, we just choose a number between 0 and 1, so a fraction, it would move much slower. And if we wanted our smiley face to go clockwise, all we have to do is add a negative number in front of our model.time function. So I'll change the speed to 50, just so you'll be able to see it better. But now he's moving much faster. And that's sort of the gist of how we're able to manipulate our rotations. So next we're going to be talking about movements. Animation refers to a picture that changes with time. In previous lessons, we applied functions such as the move function, where we're able to manipulate the placement of an object within the x and y axis. In this example, we're able to see that we have a flower, and it's actually placed in the top right corner of our screen. It's actually kind of cut off, so we'll look into ways of how we're able to move it to make it visible to our viewers. But just to refresh ourselves, so using the move function, there are two numbers in place. The first number refers to the x-axis, so the way the object is going to be moved in terms of left and right. The second number refers to how we're going to move our object in terms of up and down, so the y-axis. We're able to enhance these numbers we previously assigned as coordinates to be further decorated with the function model.time, some variation of it, to bring our move function to life. This new function with model.time creates a movement that interacts with time that has passed since the compile button has been pressed. So as mentioned previously, model.time refers to the number of seconds since the compile button has been hit. To demonstrate movement, we're going to be moving our flower around and trying to animate it to go up and down, left and right, and even diagonally. So to begin, we're going to look at our move function we have right now that centered our flower to 0, 0. What do we want to do? How are we able to move our flower left and right? We manipulate the first number, so the x-axis coordinate. And to do that, we're going to type in model.time, and that's our new function. And off the bat, since it's a positive number, it's going to move in the right direction. If we want our function to move at a slightly faster pace, we're able to multiply our function by a number greater than 1. If we want our number to move slower, we're able to multiply it by a fraction, so a number between 0 and 1. Then it moves slightly slower to the right. If we want our function to move in the left direction, we just have to multiply it by a negative number. And I'll multiply it by 25 so you can see the speed better. And we can do the same thing if we want our object to move up and down, so in the y direction. So for now, I'm going to move it back to 0, and we'll apply the same function to the y. And as we see, our flower is moving very slowly upwards. And if we want it to move downwards, we'll just put a negative in front of model.time, and the same thing happens. Now, what happens if we want our flower to move diagonally and the upper up and to the right? We can apply a model.time to both the x and the y and see our flower move very slowly upwards. And we can even speed it up by timesing it by 50. And there you have it. Now, with this in mind, can you try to make the heart group you created in lesson 1 and have it move to the top right of your screen as well?
Hi, I'm Jiwoo, and I will continue where we left off in movement animation. So notice how we have a problem here with our code because, as you can see, it results in an infinite movement of our flower. If you want to achieve a movement animation that stays within the frame of our view, you may want to use something called trigonometric functions. Trigonometric functions are typically taught in high school, but in this lesson I will teach you some basic properties to help you understand how repetitive motions work in Elm programming. Now, to better visualize what trigonometric functions are, I'm going to go to Shape Creator, and on the bottom I'm going to choose this icon. Now here you can see a sine function, which is a special type of trigonometric function. Basically what a sine function does is that for any input it gets, for example in this case it will be modeled at time, it always output a value between -1 and 1. And as you can see from the graph here, the sine function increases and decreases its value over regular intervals and never go infinitely high or infinitely low. So it repeats its value over regular intervals, and this is exactly the property we need to make our animation stay within the screen. Now going back to our example, instead of move 50 times model.time, I'm going to say move 50 times sine model.time for x and then 0 for y. So now the flower once again moves in horizontal direction, but instead this time it repeats right and leftward movement and never go outside of the screen. There are two properties of sine function I want you to be able to modify in this lesson. First one is the magnitude, and the second one is speed of movement. So the general structure of sine function is, I'm going to write for you, I'm going to write a multi-line comment, is A times sine, B times model.time, where A is magnitude and B is speed. So instead of 50, if I write 100 here, the magnitude of our movement will increase. And here, if we take our model.time and multiply that by some number greater than 1, for example 5, the speed of our animation will increase. So as an exercise, I want you guys to try modify this value for A and B and see what it does to our animation. One of the cool animation you can make using trigonometric function is making a circular movement. In the previous example, we learned about sine function, but there are other functions that make up the family of trigonometric functions. To make a circular movement, we need to use something called a cosine function. So on line 7, you see that I've slightly modified our code so that on the x-coordinate it takes sine function, and for the y-coordinate it takes a cosine function. And I've multiplied both the cosine and sine functions by 30 to increase the magnitude and better visualize the movement. So what is a cosine function? A cosine function has the same property as a sine function, but with a different starting point. So here I've drawn a very simple graph of our sine and cosine functions. As you can see, our sine function and our cosine function start from a different point. And our x-coordinate here simply means model the time. So when model the time equals 0, our sine function is at 0. And notice that in our code we said x-coordinate takes sine, y-coordinate takes cosine. So for x-coordinate we would have 0. And cosine function when modeled at time equals 0 is 1. So our y-coordinate when modeled at time equals 0 will be 1. And if we take this and plot it in a different xy plane, we get this point right here. So when modeled at time equals 0, we start from this point. And then we move on. What happens when modeled at time equals 90? When modeled at time equals 90, our sine function is at 1. So our x-coordinate will be 1. When modeled at time equals 90, our cosine function is at 0. So our y-coordinate will be 0. And if we plot that, it will be this point right here. So from 0 to 90 seconds, we've traveled along this line like that. And then we move on. And then when modeled at time equals 360, we go back to our initial starting point. So our x-coordinate is at 0 and our y-coordinate is at 1. And this is exactly the same as our initial starting point right here. So from 0 to 360, we've traveled along this graph, along the circular graph. And that's how we achieve this circular movement. But now you may be wondering why it takes such a long time, 360 seconds, to make a full rotation. In reality, both our sine and cosine functions take a unit called radians. So if we take, for example, 360, model the time equal 360, and if we convert that to radians, it would be 6.28 radians. So it would take only 6.28 seconds to make a full rotation. So we went over how to use a trigonometric function to animate movement, but what else can we do with what we've learned so far? In our shape creator, there are a bunch of examples showing how to use trigonometric function to create various animations. For the next example, I'm going to use the scale function to create a heart beating animation. So on this animation slot, I've prepared a code for the heart used in one of our previous lessons. And I'm gonna say here, scale sine model.time. So our heart is beating, but we have a problem because our heart flips upside down at some point. And this is because sine function, as I explained before, ranges from -1 to 1 for any given input. So from this graph here, you can see that from 0 to 180, our sine function is in our positive zone. But from 180 to 360, it goes down to the negative zone. So what happens in our scale is, I'll let you comment. Nope. It goes like scale 0, scale 0.5, scale 1, scale 0.5, scale 0, but then it goes down to the negative. So it says scale -0.5, and then scale -1, scale -0.5, and then it goes back to 0. So this negative scale is what causes this heart to flip upside down. So to avoid this problem, we need some way to convert these negative values to a positive value. And for that, we're gonna use something called absolute value. So we can say ABS for absolute, and then put bracket around sine model.time. So basically what an absolute value is, it is simply the magnitude of a number without its sign. So -0.5 becomes just 0.5, -1 becomes just 1, -0.5 becomes just 0.5. So in our graph, it will look like this is gone, and we would have this kind of graph, where these negative numbers are converted to positive number. So our range changes from 0 to 1 instead of -1 and 1.
The last concept we're going to discuss is color theory and how we are able to make our own custom blend of colors within Elm. In school, many of you may have learned about primary colors, colors that cannot be created by mixing other colors and are instead used as a stepping stones to create other colors. Traditionally, these colors are red, yellow, and blue. However, the term primary used to describe them is relative to the space in which the colors exist. In biology, we learned that the colors we see are based on our body's response to light, as filtered by the eye, which contains 3 receptors or cones that respond to the different light waves. These colors are optimal in the sense that they are able to create a wide range of colors visible to the human eye by mixing light of these colors, which we call as additive primary colors. So we have red, green, and blue instead. Within Elm, we have various ways of creating color. So if we're able to click on our shape creator, we begin with our solid colors. But say we wanted to create more or have a wider range, we're able to change the hue we see based on these little arrows. And once we start manipulating them, we see that our code changes from being simply filled black to filled RGB and then a set of 3 numbers describing them afterwards. RGB is a different way of creating colors, which I'll go through now. So RGB stands for red, green, and blue, and intensity of color is represented in values ranging from 0 to 255. Let's play around with the different numbers to get a better understanding of what each color and intensity means. So we have a few tools to figure this out. So if we go back into our slot and we click on colors, it'll take us to this really interactive page called Flashlight, where we're able to play around with the different colors present and how we're able to view them. And a code will pop up at the bottom that you're able to simply copy and paste into your slot as usual. If you're looking for a more fine-tuned version of colors, you're able to go onto Google and type in RGB color picker. Through this tool, you're able to more so fine-tune your colors and determine what hue you want exactly, going along the grayscale. So what happens if we're putting all of our numbers to 0 except for our first one? We get a really bright shade of red. So as I said before, RGB stands for red, green, blue. So the first number correlates to your red scale, the second to your green, and the last number to your blue. So if we're able to put our first number back to 0 and maybe only change our green, we get a really bright shade of green. And if we were to do the same to our blue, we get a really bright shade of blue or cobalt when we silence our red and our greens. Additive mixing of red and green light will produce shades of yellow and orange, mixing green and blue will produce shades of cyan, and mixing red and blue will produce shades of purple and magenta. When you mix equal shades or equal proportions of additive colors such as green, blue, and red all set at 50, you're going to get a shade of gray. When all these colors are fully saturated, so when all of them are set to 255, you're able to see that our result is white. So now, what happens if we have all of our colors set at 0? Yeah, we result with a shade of black, or black, no color at all. So now that we have this new tool, we're able to copy and paste this new code into our slot as before, but just make sure you're removing the commas in between and we're following this format we have, where we have RGB, your red scale, your green scale, and then your blue scale. And if we go back to Shape Creator, we're able to see our custom, or our generic colors again. And as you can see, we have 3 options for orange. We have orange, dark orange, and light orange. These colors are a great base point, but if we ever wanted to change, or maybe your new task can be, can you find or create a color using the new tools we have found to create a shade of orange that you'd find within a sunset?
Another model you can use to represent color in Elm is HSL. So HSL stands for hue, saturation, and lightness. Hue is basically the color, and saturation is the purity of color, and lightness is brightness. color. And the units are degrees for hue, percentage for saturation, and also percentage for lightness. So notice how, unlike RGB, hue takes degree as unit of input. So when hue is equal to 0 degrees, the color is red. And if we go 120 degrees, the color is green, and 270 degrees will give you blue. But if you go a full rotation and say degree is equal to 360 degrees, then it will give red once again. The way we write HSL in Elm is pretty simple. We write HSL, and then we write degrees since we know the unit of hue is in degrees. And let's try 0 degree. And then saturation, we're going to give 1, meaning 100%. And for lightness, 0.5, meaning 50%. This will give red as expected. Now let's change the degrees to 120 degrees. It will give green. Now for blue, it is 270 degrees. So if we do 270 here, it will give blue. And then if we go full rotation and say 360 degrees, it will give red. And if you decrease the saturation value here from 1 to, let's say, 0.3, it will give a dull color. Now if you change the brightness and you decrease to something low, 0.2, it will give a darker shade of red. And if you increase the brightness, it will give a lighter shade of red. The nice thing about HSL is that saturation and lightness can remain unchanged, and you can only use hue to animate colors. To make colors change over time, we can once again use the concept of model.time. So we're going to start with RGB first, and we're going to change the color of red. You write RGB, and then I'm going to multiply model.time by some constant to speed up the process. And then give 0 for both green and blue. Let's see what that does. So we start from black, and then the color gradually changes from black to red. And it remains red for the rest of the time because remember, RGB goes from 0 to 255. Anything beyond that just stays the same. Now if we use HSL instead, we get an interesting animation. Let's try. So HSL, same thing, but degrees, 30 times model.time, 0.5. For HSL, it creates a rainbow-like effect because, once again, hue is in degrees. So when you do a full rotation, you would always go back to the color you initially began with. So in this way, hue, HSL, is a better model for animating colors in Elm.
Now that our lesson has come to a close, I hope you learned a lot and gained a few new skills. So why don't you try adding some of these animations to your basic shapes that you made in lessons 1 and 2. This can look like maybe adding a winter scene or some falling snowflakes to the background of the snowman you created in lesson 1, or maybe even using the smiley face we created in this lesson and having him go around a couple other smiley faces, or maybe even creating your own Pac-Man scene. The possibilities are pretty endless, so we encourage you to get creative, ask questions, and don't forget to share your results with your family and friends using this link, or even typing in the bottom right-hand box and letting us see what you've been up to. And we'd love to be kept in the loop and maybe even sharing it to our website.